In today's tutorial we will have a look at the hydrolysis of this allylic chloride. It's a reaction from which we can learn a lot if we have a closer look to the mechanism. So the result of this reaction will be a mixture of these two allylic alcohols. So to the mechanism, water is not nucleophilic enough to directly substitute that chlorine, but it is a very polar solvent. That means it enables the allylic chloride to fall apart into its ions, the chloride anion and the carbocation, which is stabilized isomerically. We have on the one hand this structure, a primary carbocation, on the other hand the secondary carbocation, which is somewhat better stabilized due to the inductive influence of that CH3 group. As we know, the truth lies in between, but more close to that one because of the better stabilization. So we can draw that as this, such an allylic cation, and now we can say, well, because this has more share of the truth than we have here, a higher share of the positive charge than here, we draw that delta plus here somewhat larger than on the other side. So overall we have more positive charge density on that part of the molecule, and therefore if a water molecule approaches this carbocation, it will more easily be orientated towards this center. And it will then react faster or more often here than there. And that means this one, C prime, it will be formed kinetically to a higher extent than that one. And finally, also after deprotonation, we will end up at the secondary alcohol, kinetically favored. However, since here with the primary alcohol, we have less sterically crowdedness and moreover a double substituted olefin. Therefore, this is the thermodynamically favored product. So, if we run this reaction rather short time, then we will predominantly become D prime as the product, the kinetically favored one. If we let it run for a longer time, then we will get far more of that one, simply because all those reaction steps are reversible. So if this has been formed, it can react to that and then also to the carbocation, and then we into the other direction here to this one and forming that. Well, actually, if we have HCl in excess, then it would be a method to produce A or A prime with the chloride here in this direction of that mechanism. So let us have a look at a diagram having here the energy, and there we have the reaction going on in this direction. So, where should we start with the energy niveau? First, energy level here, A. Somewhere here we have to pay attention that the products D, since this is nicely, smoothly proceeding, the product's energy levels should be lower than the starting point. So, from A, via a transition state, we will get to the reactive intermediate B, this one. So, then C prime is kinetically favored, as we already mentioned, because H2O will predominantly faster access this position. That means that we have a relatively low energy barrier to get to C prime, but C prime is on a higher energy level than C. This one, this is thermodynamically more stable. On the other hand, to get to C, this is the slower reaction. That means we have to draw here a higher energy barrier to get to C. Then the final deprotonation to D prime and D. This is in both cases a very fast process. It's simple to deprotonate such a position. Thanks for listening.